Last time we went over what the derivatives of the 6 trig functions are, and now we're going to look at some examples. So find the derivative of y equals 3e to the x cosine x. So first of all, we just want to, like always, be conscious of all the other derivative rules that we have learned, and right here we have a situation of a product of two functions of x. We have an f of x times a g of x. So we need product rule. Now you have two choices with the constant multiple of 3. You could just basically factor it out in front of this whole thing that we're going to put in for the product rule, or you could just lump it in with really either function, but conveniently with the first function e to the x, which is what I have shown here, and that's what I'm going to do. So as we think about taking our derivative, dy dx, we want to think about our structure is the product rule. So we're going to have f left alone, and then times the derivative of g, and then plus we'll change that order, g gets left alone, times the derivative of f. All right, so excuse me, let's take a look. So f of x is our 3e to the x, g prime. All right, the derivative of cosine of x, that is the opposite of sine x, so negative sine x. Plus, change that order, now it's g of x left alone, so cosine of x left alone, and then times the derivative of f, constant multiples get carried along, and derivative of e to the x is e to the x. So what we end up with here is, if we wanted to, you might see a lot of times where in a final answer, maybe they factor out a common factor. You wouldn't have to, you could have left it, but if I factor out 3e to the x, I could write this as then times the quantity of, and just putting the positive term first, cosine of x minus x. All right, let's look at another one. So essentially, we're just going to be asking similar types of questions that we've already been working with, but now just involving our new trig functions. So let's find the slope of the tangent line to the function g of theta equals theta times 1 minus secant theta at theta equals pi over 3. All right, so once again, looks like we have a product rule. And even if you were thinking, well, I'm just going to distribute theta, the problem is you would still have a product rule in the second term, which is fine to do it that way. I'm just going to go ahead and leave this like it is, and I'm just going to apply product rule on this outermost structure. So I have theta being multiplied by the 1 minus secant of theta. So that's what I'm going to do. So let's go ahead and do this. So g prime of theta is going to be, let's say the first function left alone, so theta, and then times the derivative of the second factor. Derivative of 1 goes to 0, of course. The negative gets carried along as a constant multiple, and the derivative of secant of theta is secant of theta tangent of theta. And then plus, we change that order. We leave the second factor, the 1 minus secant theta, that function alone, and then times the derivative of theta, which is just 1. All right, so there's what we have. There's not a lot of simplifying. There's nothing to factor out here. I mean, if you want to just kind of clean it up, you could maybe just say negative theta, secant theta, tangent theta, and then just plus the 1 minus secant theta, something like that. In any case, we're really looking for what is the slope of the tangent line evaluated at theta equals pi over 3. And of course, that's the same thing as just notationally saying that I need to plug pi over 3 into my derivative. So that's what we're going to do here. So kind of either of those notations, you wouldn't need them both, but I just want you to see a lot of both. All right, so we start by plugging in theta, so negative, in for theta, pi over 3, and then secant of pi over 3. Well, in order to evaluate secant, I'm really going to need to think of it as 1 over cosine. So I'm going to go ahead and just write it that way. So 1 over cosine of pi over 3. And probably the same thing here, breaking down tangents and thinking of it as sine over cosine of pi over 3 in both of those. And then plus 1 minus, and once again, secant, I'm going to think of as 1 over cosine of pi over 3. So you need to be able to evaluate these exactly and not just go to decimal approximations. We only do that if we are prompted and we're told, to round to a certain number of decimals. All right, so thinking about your unit circle, and if you have to, drag it out and take a peek at it, do that, but you really want to be able to refamiliarize yourself with your unit circle here. So cosine of theta, so negative pi over 3 times 1 over. So your x coordinate up there at 60 degrees, if you want to think of it that way, that's just your 1/2. And your sine up there at 60 degrees at pi over 3 radians is the root 3 over 2, again, over the 1/2, plus 1 minus, again, the 1 over the 1/2. So any of these situations where you're dividing by a fraction, that's like multiplying by the reciprocal. So 1 over 1/2 is really 2. The root 3 over 2, again, divided by 1/2 is really multiplying by 2, plus the 1 minus the 2. So looks like we're going to end up with, in this first term here, negative 2 pi square root of 3 all over 3. And then the plus 1 and the minus 2 is going to give us a minus 1. So that would be okay. If you wanted to think about writing this all as one term, you could of course think about, the 3 over 3, rewriting 1 as 3 over 3, and then you could say this would look like negative 2 pi square root of 3 minus 3, and then that whole thing all over 3. So either of those would be the exact form of the slope of our tangent line at theta equals pi over 3. Okay, number 3. Let's take it one step further here. Let's look at an equation of a tangent line. So last time we just did the slope. Let's take it again and go to the equation of the tangent line to the curve. F of x equals 2 tangent x at x equals pi over 4. So to find an equation of a tangent line, of course, the first thing we're going to need is going to be the slope of that tangent line. So that means we need our derivative. Constant multiple gets carried along. Derivative of tangent of x is secant squared of x. And again, if I want to know the slope, I'm going to just kind of draw that right here and say evaluated at x equals pi over 4. So now, if I think about subbing this in, again, secant, in terms of its reciprocal, is like 1 over cosine. So I'm going to have this 2 over cosine of pi over 4, quantity squared. Now, if you remember in your unit circle, I'm sure you do this one, your cosine of pi over 4 is root 2 over 2. That's just the rationalized form of 1 over root 2. And when they're in denominators, I kind of like to use the 1 over form because eventually I'm going to multiply by the reciprocal. So you could use either of those and you'd get to the right answer. But I think in a situation like this, when it's in the denominator, the 1 over root 2 becomes the easier form to work with. So I have 2 over 1 squared is 1, and then root 2 squared is just a half. And then multiplying by the reciprocal, of course, we're just going to end up with 4. So this is our slope of our tangent line. Now, of course, the other thing that we always need is the xy ordered pair. And so in this situation, all we had was the x coordinates. Sometimes they give you both. A lot of times here, I'm just giving you one. And so that always means that we are subbing this back into the original function, f of, in order to get the y coordinates. So we have our pi over 4, that's my x coordinate, and then 2 times the tangent at pi over 4. Well, sine and cosine are both root 2 over 2. They're the same at tangent, so that sine over cosine of pi over 4 is just going to be 1. Tangent pi over 4 is 1. So we're going to end up with our ordered pair here being pi over 4, 2. Okay, so here's our xy ordered pair. And now, of course, we're ready to go to find the equation of our line. So our y minus our y coordinate is going to equal our slope, and then the quantity x minus our x coordinate. So y minus my y coordinate here, we just found out was 2. The slope was 4. Quantity x minus our x coordinate there is pi over 4. And then just kind of finishing this out, doing a little bit of distributing, we would have 4x minus, those 4's would reduce, and we would just have pi there. And then, of course, just our last step, just simply adding 2 to both sides. We're going to end up with our final answer here, y equals 4x plus 2 minus pi. And again, you want to leave it in an exact form unless you're prompted to, like I said, go to a decimal approximation. All right, moving right along here, number 4, for what x does f of x equal 5 sine x plus cosine of x have horizontal tangent line or lines? So this is another common question. So here we're not looking for the slope of the tangent line at a particular point. We're trying to find where the slope of the tangent line is equal to a particular slope. So here we're trying to find, we want to know where the slope of the tangent line is equal to 0, because of course that's what it means to have a horizontal tangent line. Is going to mean that its slope is equal to 0. All right, well, slope of the tangent line, that simply means the derivative. Okay, so slope of tangent line, that's my derivative. And my derivative in this situation is 5 carries along, derivative of sine of x is cosine of x, and then derivative of cosine of x is minus sine of x, and we are now looking for where that equals 0. All right, well, if I add the sine to the other side, I'm going to have 5 cosine of x equals sine of x. And if I divided both sides by cosine then, so first I added over my sine of x, and then if I divide both sides by cosine of x, I'm going to have that 5 is equal to sine over cosine, which is tangent of x. So in this situation, a lot of times when we solve trig equations, you might first get everything in terms of sine and cosine. This already was. We'd probably next look to see if we can factor out a GCF, and in this case we couldn't. So here we were just kind of trying to isolate for a single trig function, and we're able to get that there with tangent of x equal to 5. Now, if I have tan x equal to 5, I'm trying to think about like where is tangent equal to 5, and that's not a nice point on my unit circle. So I'm going to need to use my calculator here, and that's going to mean needing to first, let's write this as kind of taking our tan inverse here of both sides. And so I'm really going to be looking for where I'm looking for where tangent's equal to 5, and that of course is saying tan inverse of 5. Now let's think about this for a second before we kind of jump in and do it exactly here for this value of 5. So what I want us to think about here for a second is, what if this was an easier point? So just for a second, suppose that we had something much nicer, tangent of x equal to 1. Now certainly we could do this on our calculator, so that's the same thing as saying in our calculator we could do tan inverse of 1, but this is something that we actually know just from our knowledge of the unit circle. Where is tangent equal to 1? Well, there's 2 places where tangent's equal to 1. The first one is in the first quadrant at pi over 4. And then the next one is down in the third quadrant there, and that's the 5 pi over 4. So those are the 2 places where sine and cosine are equal. But then you could keep, so those are exactly pi units apart, pi over 2, sorry, pi over, no, pi, I said it right the first time. Those are 180 degrees apart. Those are pi units apart. So we could, kind of keep going in this case in either direction. But what are we really doing in this situation? We could go back even to the first value, the initial value at pi over 4. That, by the way, is going to be the answer that we would get in our calculator. The calculator would give us the decimal form of pi over 4. So that's what your calculator is going to give you. So if you type this into your calculator, tan inverse of 1, you get pi over 4. We now, thinking about our unit circle, know that these, all of the infinite set of answers, yes, pi over 4, but then add or subtract any k integer multiple of pi. So if we had that, that would cover all of the solutions. And in this situation, the domain was not restricted to just the interval from 0 to pi, so I do need representation of all of the possible solutions. So this is the key observation that I wanted you to kind of be able to observe with some slightly easier values here, which is that if you are using your calculator, you need to take that answer and add k pi, where k is any integer. So essentially, the exact form of our final answer would really be kind of exactly that. So x would equal tan inverse of 5, and then plus k pi, where again, k is any integer. Now, if we really, that's the exact form. If we really want to see what it looks like as a decimal, then we'd have to go to our calculator. But again, radians and decimals a lot of times don't have a lot of intuitive meaning in our heads. We're so used to degrees from years of working with degrees. But you could look at it in your calculator there if you wanted to. But that would be the exact form on that. All right, one last example here to wrap up our derivative examples with trig functions. And so on this one, we have y equals theta times cosecant of theta. And we are going for the second derivative. But of course, that means we need to start with the first derivative. And so once again here, I have a product of two functions of theta. So I need to use my product rule. All right, so let's go ahead and jump in with that. So first function left alone, theta. Derivative of cosecant of theta is negative cosecant of theta cotangent of theta, plus, change that order, cosecant of theta left alone times the derivative of theta, which is 1. All right, so in terms of simplifying, I do want to do whatever simplifying I can on the first derivative because I have to go on to take the second derivative. If I leave this first term as negative theta cosecant theta cotangent theta, when I take the derivative of that first term, if I leave it like it is, I'd have to identify like an outermost product, but then within one of those products, I would have another little product rule. So I'd have an outer product rule, and then within that, another product rule, which would be okay. But it would be easier to factor out a GCF, or no, if it's greatest common factor, a common factor. The only common factor we can factor out here is cosecant of theta. And then in parentheses, from the second term, I like to put the positive term first, I would have 1. And then in the first term, I would have minus theta cotangent of theta. Now, it looks like I am still going to end up with a product rule within a product rule, but I just think that this structure is going to be a little bit easier to kind of work under on this one. So that is what we're going to work with. And we're also kind of starting to get used to this idea that a lot of times simplifying derivatives involves factoring, and because a lot of times as we move into later chapters when we're working with these and setting them equal to 0 and so on, we are going to like factored forms. So we're kind of getting into that habit as well. So let's now go on to take our second derivative. So we will have, first of all, our outermost structure here, and so I am going to be a little bit clearer on this one than I was on that first derivative, because I am going to have two product rules happening here. So I'm going to have, f of theta, and then it's going to be times g prime of theta, and then it's going to be plus the g of theta left alone, and then times the f prime of theta. So let's start with that outermost structure. All right, so f of theta, so first function left alone, cosecant of theta, times, now g prime of theta. This is where I'm going to have a product rule within a product rule. So derivative, of course, of 1 is going to go to 0. But when I get to this second term, I have a product of this theta and the cotangent of theta. So this is going to require its own little product rule. So let's say I call this function h and this function k. So within my kind of structure of what I have here, of course, the derivative of 1 went to 0. I'll just kind of write that well, I don't need to write that, but derivative of 1 went to 0. Now, in terms of the negative, it's like any other constant multiple. You could bring it out in front of the quantity of your product rule. I tend to just lump constant multiples in with my first factor. So let's go ahead and set up our product rule on this. So our inner product rule is going to be h left alone, and then times the derivative of k, and then we're going to change that order, and it's going to be k left alone times the derivative of h. So h left alone is going to be negative theta, times the derivative of cotangent is itself negative cosecant squared of theta, plus, changing that order, now the cotangent of theta left alone, and then times the derivative of negative theta, which is just going to be negative 1. So that whole quantity represents the g prime of theta. All right, now let's change that order. So plus, and this is where having the product rule kind of written out up above is helpful, because otherwise we just feel like we've done so much work, we must be done, and sometimes we might forget this whole second term. So 1 minus theta cotangent of theta, that's just g left alone, and then times the derivative of cosecant of theta, and that is our negative cosecant of theta cotangent of theta. So technically you found the second derivative. I might clean it up a little bit, even just to enter in an answer, even in your online homework portion. So let's just kind of maybe take a look at what we have. I think the less nested parentheses I have to enter, the better. So certainly on the inside here, this first term right there is going to be positive. So this would have been theta cosecant squared of theta, and then that would have been minus cotangent of theta, just to sort of clean that up a little bit. And so maybe just that, I don't know, let's rewrite and see kind of where we are here. So my second derivative, and so I have my cosecant theta here in front, times my theta cosecant squared theta minus cotangent of theta. And then I would put the minus cosecant theta cotangent theta, that monomial portion first, and then times the binomial of the 1 minus theta of cotan of theta. I mean, this at least minimizes a little bit the amount of like nested parentheses that you'd have to enter in. Is there anything to really simplify? I don't know. I mean, you could factor out a cosecant theta if you wanted to, but I'm just going to go ahead and just leave it like that and wrap this up.